programming Quadruped Robot to climb slopes using ROS2 and Gazebo. Outline. In this presentation, the question, can Quadruped Robot climb a slope, is answered. At the bottom of this page, you see a robot descending from a slope to the ground plane. So this picture implies the answer. Robot conquered the slope and now is descending back to the ground plane. In this presentation, Python program for robot climbing a slope employing ROS2 and Gazebo is offered, and its structure and usage are explained. But first of all, it is necessary to figure out if developing special program for climbing slopes is required, or the conventional program for robot walking on the flat surface will work. Programs for robot to walk on the flat surface are published in separate videos on this channel. Links to these videos are provided in the description. Next, one of such programs is trot for climbing a slope. For testing walking programs, two slopes were prepared. Firstly, smaller slope, the blue one, will be used. Robot is placed in front of the blue slope, and after the simulation program is executed, robot briefly assumes the initial pose and then starts walking. Robot approaches the slope in wide steps. And then enters the slope. Robot makes some effort, but generally speaking, it works on the slope surface exactly in the same way as it walks on the flat surface. So now robot exited the slope and continues its walk on the ground plane. Program developed for walking on the flat surface appears suitable for climbing small slopes. But will such program work for large slopes? Next, program developed for walk on the flat surface is tried for climbing large slopes. And now robot will challenge larger slope. Same simulation program developed for walking on the flat surface will be tried. After the simulation program is executed, robot initially assumes the initial pose and then approaches the slope. However, as we see, robot's attempts to climb a slope fail, which shows us that special program for climbing slopes is required. Program for climbing steep slopes was developed in this presentation. But before demonstrating its results, I would like to provide brief explanation of the programming method. To simulate leg movements, leg variable is introduced. Leg equal 1 denotes back right leg moving forward, while other legs pushing backwards. Leg equal 2 denotes front right leg moving forward, while other legs pushing backwards. Leg equal 3 denotes back left leg moving forward, while other legs pushing backwards. And finally, leg equal 4 denotes front left leg moving forward, while other legs pushing backwards. Each robot leg movement is simulated using 5 elemental moves. Each elemental move is defined by its unique set of joint angles. A variable named delay is used to provide necessary time interval for a robot to perform the elemental move. Value of the delay variable is set individually for each elemental move. This provides great flexibility for robot movement design. Typical values of the delay variable are in the range of 0.1–0.5 seconds. A loop is arranged in which elemental moves are counted. Inside the loop, after 5 elemental moves constituting one leg movement are executed, value of leg variable is increased by 1. If value becomes larger than 4, it is reset to 1. Execution loop terminates after the specified number of maximum moves is reached. The thigh, shin and leg joint angles depicted on the picture on the right side need to be specified for segments of the robot climb, namely mounting from ground plane on the slope surface, ascending the slope, overcoming the slope summit and putting legs on the other side of the slope, descending and entering the ground plane. The angles were ascertained by the trial and error method. The segments of the climb were determined by monitoring robot body height. The angle values are forwarded to the corresponding joints by use of the ROS2 forward command controller. Next, simulation results will be demonstrated. Quadruped robot briefly assumes initial pose and then swiftly moves to the slope surface. It takes some effort for robot to get on the slope surface, but after robot is on the slope surface, it changes how it walks and now moves its front legs just above the surface. Slope summit is a difficult point for robot. It overcomes it successfully. But descending on the ground appears to be not an easy task. However, robot successfully fulfills it. And now it continues walking on the ground surface. Those interested in modifying or improving the program can find the source code in the SRC Robot Control Scripts folder. Name of the source code is walk slope pi. The program is written in Python and employs ROS2 and Gazebo. Therefore, ROS2 and Gazebo must be installed prior to the program use. Program structure is simple and easy to understand. In order to modify or improve the program, joint angle values can be changed easily. Comments are provided to promote understanding of the program. Running the program. Program and files required to run Gazebo and ROS2 are stored in a folder named Walk Slope. Download the folder using the link available in the description. After download, Walk Slope folder contains only one folder named SRC. Open terminal window and move to Walk Slope folder. Execute build command. 3 new folders named build, install and log will appear alongside the SRC folder. Next, open second terminal window, move to Walk Slope folder and execute the following command: source install setup bash. Then execute launch command ROS2 launch robot Gazebo main launch pi. Gazebo simulator will be launched. Open third terminal window, execute the source command, and then execute the following run command: ROS2 run robot control walk slope pi. Robot will start moving. Note that the program was developed using Ubuntu 24.4.1 LTS system, ROS2 Jazzy, and Gazebo Harmonic v8.8. It was not tried for other versions or releases of operating system ROS2 and Gazebo. Summary. In this presentation, program for Quadruped Robot Climbing Slope is developed. Explanation of the programming method is provided. Python simulation program is offered for use. The program can be a convenient tool for learning robot programming. ROS2 and Gazebo must be installed prior to the program use.